So on behalf of Jennifer Mercer and Barry Leffer and myself, the Atmosphere Collaboration Team co-leads, welcome. This is a meeting that's being held in collaboration with the Sea Ice Collaboration Team, the Physical Oceanography Collaboration Team, and then the modeling and observing sub-teams from environmental intelligence. So it's a good group, and we're very excited to kick off this MOSAiC theme meeting. Before we do that, though, I just want to give a quick introduction, particularly for those who may not be familiar with IARPC, as to what IARPC is and what we're doing. So IARPC exists in the Executive Office of the President to coordinate U.S. federal agency efforts under the Arctic Research and Policy Act. Many of you are probably familiar with the current Arctic Research Plan and the fact that we're in the process of developing the next 5-year plan. So thank you in advance for all of your contributions to that. The current plan has 4 policy drivers related to Earth systems, Arctic resident health and well-being, environmental stewardship, and national security, and 9 collaboration teams that cover a range of topical interests, including our Atmosphere Collaboration Team. So through IARPC collaborations, IARPC brings together U.S. federal agencies with university, industry, and international partners to help accelerate progress towards the research objectives in the research plan. The collaboration teams hold regular meetings that are focused on themes, in this case, the MOSAiC theme, related to research objectives and that are associated with performance elements. If you're new to IARPC or not familiar with IARPC, we strongly recommend that you consider setting up an account on the IARPC Collaborations website so that you can stay up to date with our communications and the implementation of the research plan. And by doing so, you can join over 1,000 other people and gain access to this network to stay informed on meeting announcements, funding opportunities, and research findings. So the collaboration teams, of course, benefit from all of your participation, all of your active participation, and such participation allows members like yourselves to identify synergies and develop partnerships with other researchers and organizations. So they also offer opportunities for you to highlight your research in groups and in fora visible to Congress and federal agencies, and communicate regularly with federal program managers. So we really appreciate all of your efforts in doing that. As Meredith mentioned, we are in the process of developing a code of conduct, and we certainly hope that this meeting, along with all the others, are inclusive and welcoming, and we ask you to respectfully do your best to maintain appropriate behavior, including in the chat function of the meeting. So thank you all for being here, and let's get started. So the meeting today is focused on some preliminary findings on the air ice ocean interface as developed during MOSAiC, and we have 3 speakers with us this month who are going to provide some new insights into that. Matthew Shupe from the University of Colorado, Don Perovich from Dartmouth College and Krell, and Chris Cox from NOAA. So we're going to kick it off with Matt, and Matt's going to give us an introduction on some of the challenges and opportunities that were encountered as part of MOSAiC. And Matt, please go ahead.
All right, thanks, Heis, for the intro. I believe you can see my title slide now. Let me know if that's not the case. So I'm going to assume that most people here, if you're on the call, you probably know a little bit about MOSAiC. I'm not providing a whole lot of background. I've spoken to many of these groups many times before about this. But along the way, I think you'll get the picture if you don't know the details already. I'm going to talk about some of the challenges and opportunities from this year in the ice. And so, in short, we took this ship, the Polar Stern, froze it in the Arctic sea ice for a year as a platform for pretty intensive cross-cutting interdisciplinary research. And I'll just take you on a little picture tour of how that went to provide some context for the following presentations. I've got this plot here, this kind of map that shows the overall drift, and I will kind of walk you through the drift over the whole year. On the map, you see different ice edges. There's the kind of September ice minimum and the March ice maximum put on top of that. And the different colors that you'll see coming forward here are the different legs. And so this is for like one back last September. We packed up the ship in Tromsø, Norway in kind of late September and headed out into the ice pack. And by early October, we're establishing an ice camp there, setting up a distributed network, starting a lot of sampling programs. And we encountered a lot of really interesting and thin ice conditions. And I'll show a few photos here to kind of walk us through that process. Loading in Tromsø, here's a great picture of loading a scanning cloud radar on the ship. First time one of these radars ever been operated in the Central Arctic ice pack. This ship was packed full. It was really tremendous how much we got on board this ship. And that's one of the key highlights here is just the sheer density of science that was accomplished. We sailed off into the Arctic Ocean in search of a place to call home, in search of an ice floe. We found and explored some. We measured thicknesses, and turns out the ice was thinner than anticipated. This is kind of part of the evolving Arctic system, of course. We all know that the ice is thinning, and indeed it was thinner than we had hoped. And so we had to kind of settle at some level for an ice floe that had thinner ice than we planned. Then we started setting up all kinds of installations on the ice. Here's a nice picture of a radiation station, another picture taken from Met City as the dark descended on the whole operation out there. You can see this installation is approximately 500 meters away from the ship. We had all kinds of assets installed on the ice around the area. Here's a nice picture of an installation of a sediment trap. There were many installations like this, both around the ship and across the distributed network, some up to even 50 kilometers away in different directions to provide spatial context on the interdisciplinary kind of cross-cutting system. And then we started a very comprehensive measurement and sampling program, looking at the coupled system, the atmosphere, the sea ice and snow, the ocean, cutting across the physics, the chemistry, the biology. And one of the key themes is ice dynamics. And I say here early and often, for those that have been out in the ice, of course, dynamics are what keeps things lively. And well, it was lively right from the start. Here's a picture looking out at our kind of logistics area. You can see the gangway from the ship. This is right in front of the ship where we're trying to operate every day, and cracks are heading through camp. Another photo showing cracks that kind of separated some different installations. Near miss on Ocean City there in the blue tent. And of course, when those cracks come back together, the ridges consume things. There's power lines being consumed. So it was a huge challenge to operate out there in this dynamic ice pack. And it really required us to move a lot of installations fairly frequently, reinstall things. We had different data gaps because of this. And so this was really the first set of challenges. Transitioning into leg 2 here in yellow, this is the heart of winter time. Something that's really distinctive about MOSAiC is really getting these winter observations. This crew of people did not see the sun until they were just leaving. At this time of year, there was actually a little bit of a decrease in the ice dynamics, leading to perhaps somewhat more consistent operations, although there were certainly still challenges. Temperatures down to minus 43. And one of the great questions at this time of year is what happens to the biology? I don't have a ton of photos from this time, but this is a fantastic one showing the starry night. This is a Flux station that Chris will talk about shortly. And another great picture of some biology, some copepods here. What does happen to the biology in the wintertime? I don't know the answer to that. Fortunately, we have this fantastic data set to look at that question. Moving into leg 3, things are getting really interesting now. The Arctic circulation sets up in a certain way that really pushes the whole installation across the Arctic faster than we anticipated, much faster actually. And that's due to large scale circulation, and it led to a lot of rapid drift and more dynamics. There were some very interesting events at this time of the year, a nice warm air advection event that we're studying in coordination with YOP and the Polar Prediction Project through WMO. This is going to be an event that will be used for evaluating models and looking at processes. And of course, COVID. This is when COVID really started to set in across the globe and affect things. And it did affect the overall length of this leg, extending it up by about 2 months. So people like Chris, who will speak next, were trapped out there for 2 months longer than anticipated because we could not do the kind of rotation operations that were planned due to travel restrictions. So just a little context on this leg. This is showing the Arctic Oscillation Index over the last 7 or 8 years. And we see that in the early months of 2020, the Arctic Oscillation Index was very high. Actually, this is historically high for quite a number of months. And what this contributed to was some anomalous winds. And so we see here, this is a composite analysis of January to March relative to kind of a climatology from 81 to 2010, showing anomalous winds. And, you know, at this time, the ship was drifting from near the North Pole towards Fram Strait. And you see this bullseye of anomalously high winds that are basically pushing the ship further along its course. And that got us ahead of schedule. But it also provided this opportunity to look at what's happening with our installation there with this kind of larger scale structure that's set up in the Arctic at this time. And of course, dynamics, right? As we're moving rapidly, there's all kinds of dynamics in the area. And so you see a lot of the kind of different lead and ridge structures here around the ship associated with this kind of shear zone that passed through the area. Here's another great shot showing the challenges that we face with just keeping these instruments operational. That's Met City in the background. You see a tower there. You see a number of leads in between, and this attempt at extending power lines across these, you can just imagine that this is really hard to keep things on track. So the transition between legs 3 and 4 due to COVID actually required Polarstern to come out of the ice to meet the resupply. And that caused somewhat of an interruption to some of the measurements, although we had a lot of drifting autonomous assets out there that continue making measurements. So there was the continuity, but some interruption due to COVID. And then the return on leg 4 to capture the melt season and to observe the ice flow all the way up to the ice edge. So let's take a little look there. One point I would like to make, though, is that, you know, the ship had to come out of the ice, and that was not planned. So, you know, a little bit of a challenge there. On the other hand, especially from the atmosphere perspective, and I know one of the teams here is the atmosphere team, a lot of the equipment was installed on the ship itself. Looking at clouds, sampling air, launching weather balloons, things like that were all from on board the ship. And so those were continuous throughout this whole time period. And we actually had the opportunity of the ship transiting from within the ice pack out to the edge and back, which, you know, I'll call some bonus measurements, things that we didn't expect to have that we actually get. And those transitions across the ice edge are actually really interesting and useful. So again, an opportunity there. This was the MOSAiC Flow 2.0. This is the return to the flow at the start of leg 4. And this is what remained of the original MOSAiC flow. It's about 1 kilometer across. And in this picture, you can see a couple little installations on the ice of our camp. And you see that the melt season is really setting in. A pretty cool perspective on that is here. This is a laser scan from the helicopter. And I kind of put in the boundaries of the ice flow there. And you can see the ship. And you can see in the kind of brighter colors, these are the ridges. In the darker colors, these are the flat areas and melt ponds. So lots of texture to this flow. And then here is just to kind of illustrate the amount of science we're doing. These are all the different sampling areas and activities that were going on during this time of year. We had a whole region of first-year ice, the kind of thinner ice that had formed over the course of the year for looking at things like albedo and melt ponds, for taking ice cores. All kinds of other installations like the Met City area for looking at the atmosphere, the Ocean City area. We're flying drones at different locations. There's a bunch of remote sensing, kind of ground validation instruments, and all kinds of other activities around this ice flow. So just, again, packed with great science. Lots of ice coring and other sampling going on. Here's a nice picture. I see Melinda's on the call here, doing a transect around the flow to measure thicknesses from the ice, melt pond depths, snow depths, looking at the reflectance of the surface on all these different ice types as the melt season really progresses. Measuring up in the atmosphere with tethered balloons and towers, all kinds of different sensors. Here's the Ocean City, sending instruments down into the ocean to look at the ocean structure. And in the background, that's a group flying unmanned aircraft in the atmosphere. This time of year was actually really interesting, right? The snow and ice is melting. dumping a lot of fresh water into the ocean. That fresh water sits on top of the salty water, creating this freshwater lens that affects all kinds of things like the transfer of heat, the transfer of gases, transfer of nutrients. The interface was a real biological hotspot. So it was a very interesting time of year that we captured pretty well, I think, and I think we'll learn a lot about this kind of melt process and how that affects the structure of the ocean. Now, leg 4 actually reached the ice edge. We did not plan on this. This rapid drift pushed the whole thing much further than anticipated. We hoped to be there within the ice pack for the whole year, but instead came to the ice edge at the end of July. But again, this was an opportunity. We got there. We actually pulled our equipment off the ice the night before the ice flow just totally disintegrated into 1,000 pieces. So all the way up to the very end, we measured this ice flow to the very end of its life cycle. So that's, again, a really amazing opportunity kind of embedded in this challenge. But then we handed over to the next crew, the leg 5 crew. Well, we still had some time left in the year. And so that crew took the ship back up close to the North Pole to capture the last part of the year, to capture the freeze up. Of course, installations at that time were challenging with the ice minimum, lots of melt ponds, things like that. But the installations were made in a way to really do a great job of capturing the freeze up. And I think that we did do a great job of capturing this freeze up and the processes involved in that to really bring this full circle, to capture all the seasons of the MOSAiC year and how that affected the sea ice and all the other processes. A brief statement on modeling activities. There were tons going on and are tons planned. More than 70 discrete modeling activities are in the modeling plan for MOSAiC. One is kind of noted here, a web page that was run through NOAA to do some kind of near real-time model verification using observations from the field to evaluate processes and models. There's a lot of collaboration with the YOP activity through the WMO to develop data sets that are pulling from the various observations to package them in a way that can be used to evaluate models. So lots of great modeling activity. This data set will really help to achieve that key objective that MOSAiC had to really push our modeling capabilities forward. Also from the outreach perspective, really tremendous opportunity. I'm not going to dive too deep in here, but just to say that we have planetarium shows, documentaries, all kinds of curriculum for different age levels, online courses, tons of media engagement. I'd really encourage you to look for some of this content. It's really amazing content from the field from so many different perspectives. By the numbers, we had 20 nations involved in funding this activity, and more nations if you count the people individually that were there. 7 icebreakers or ships involved, more than 60 institutions, more than 400 people actually go into the field. $150 million total budget, and really that's a pretty big underestimate at this point, and more than 40 million from the US. So to summarize here, MOSAiC was characterized by challenges. And apart from COVID, these can really also be viewed as opportunities. We were in a thin and dynamic ice pack, and really there, seeing it evolve and seeing it manifest itself. We had so much science packed on the ship, packed on the ice, and a broad participation from the international community, interagency contributions, interdisciplinary cutting across all types of science. And we built a ton of capacity with so many new researchers being introduced into field research and developing concepts for how do we actually conduct research on this emerging thin Arctic environment. So with that, I want to thank NSF, DOE, NOAA, NASA as our major US contributors to this. And of course, the Alfred Wegener Institute, the lead institution here. They provided the ship and so many other resources. Together, these institutions and many others internationally really made this happen. Please follow the information. You can see some great web pages there. There's lots of information available. And with that, thank you.
Great, thanks very much, Matt, for that really nice overview. Clearly a lot to talk about and a lot to think about for everybody. I will allow a little bit of question time here so that we don't have to save all the questions for the end. So if you have a question, if you're willing to use either the raise hand function or I believe we're going to reactivate the chat here for a few minutes, so that if you'd like to type a question into the chat, we can do that as well. I'll give people a minute or two to type or again, we're pretty friendly here, so feel free to raise your hand and speak up if you do have questions for Matt about the expedition as a whole, or about some of the specific things that he highlighted along the way. So there is a question in the chat asking if anyone fell into a lead.
There's many answers to that. Yes, people got wet in numerous ways, and that's all part of the story. You have to be up close and personal to really get those views. And so, yeah, there were definitely people getting wet, but we all had great, survival suits that would float and keep us warm and safe, and nobody really had a major injury because of this.
Thanks. There's a second question asking you what surprised you the most about your research findings?
Well, I would say from a findings perspective, we haven't found our findings yet. I mean, there are things that have emerged, of course, but we have so much to do to really dig into the data. To me, I've been out to the Arctic sea ice quite a bit, and it still surprised me with how dynamic it was. And I think that that's really just part of this emerging Arctic system. And the fact that something so obvious, right? We know the ice is declining. We know it's really breakable. Something so obvious could still kind of be out ahead of us a little bit, to me was surprising. But then also to see all these fantastic ways in which the system is related to that. How does this affect, this fresh water going into the Arctic Ocean, or how does it affect the mixing processes? To me, I think that I'm just really excited to dig into these data more, and I know that the community is as well.
All right, there is one other question, and that is whether there are any published resources related to the data collected.
Right now, not so many, but those things are being developed as we speak, right? So we have a pretty comprehensive data policy. We have a full kind of program from end to end for data management and data archival, working with multiple archives. And so all these things are planned, of course, with very comprehensive metadata to document all this. And then as well, we really want to have data special issues to really highlight these specific data sets. And so all of this is planned. We've talked a lot about it, but we really are in the phase now where we start to pivot towards our management of our data, documentation of our data, and getting it out there publicized so that the general public can be informed.
Thanks, Matt. I think you just answered Marianne's question as well about how they're archived and distributed to the community. So I'll move on to the next question here about when you did the in ice to out of ice transect, which data were being collected?
Yeah, that's great. So I assume you mean in the rotation between legs 3 and 4. And a lot of observations were being collected as long as we were outside of the 12-mile area from Svalbard. And so this is a lot of the operational equipment like radars and lidars, so for looking at clouds, a lot of the equipment for sampling air to look at aerosol properties or trace gases. Of course, radio soundings occurred and sometimes intensified when we were passing certain boundaries that were very interesting. There was underwater seawater that was collected. So many of the measurements could carry on over the course of those transits in and out. I also, of course, from the sea ice community, there was a number of remote sensors looking down at the surface as we transect through the ice. So yeah, many observations that we're able to make those transects.
All right, and we've got one last question before we move on to our next presentation, and that is that it took 12 years to get MOSAiC out and back from ASCOS in 2008. What is your simplest word of wisdom?
Oh, Patty, yeah. Wow, word of wisdom. Yeah, it's a huge challenge to a career to invest this much in something like it, but hopefully, and we'll see, hopefully it brings about great benefit for the community. And that's, for me personally, the reason I invested so much in it, and so many people invested so much in this. And I think ultimately that's what it takes. It takes a lot of people putting a lot of time and effort collectively to make big things happen. And hopefully we get really big results out of this big project.
Very good, thanks, Matt. There are some other questions coming in, but I think we're going to have to move on to the next presentation. And perhaps when we reopen the chat, Matt, if you see one or two more there that were not answered, you could just drop a note in there. We were going to shut the chat down for a few minutes during the next presentation. Our next presenter is Chris Cox from NOAA in Boulder Physical Sciences Laboratory, and he's going to talk about some of these early findings on observing the surface energy budget over the Central Arctic. So Chris, please go ahead.
Thanks, guys. Can you hear me okay? I'm just trying to share my screen.
I can't hear you. I will note that during Matt's presentation, some of the slide transitions, at least on my end, were lagging a little bit. So, he was pointing to things that were on the next slide when the next slide wasn't there, but it wasn't, it was a few seconds. So just be aware that it may take a few seconds to transition between slides.
Yeah, I noticed that as well. So can you see the title slide all right?
Yep, looks great.
Okay, great. Thanks, guys. So as I said, I'm Chris Cox. I'm with NOAA's Physical Sciences Laboratory in Boulder, Colorado. So I was out at MOSAiC during one that was in particular the first half of leg one. This is the part of the deployment leg, if you will. And I was on the Fedorov deploying the distributed network with that team. And then I was back at MOSAiC for leg three, which was roughly the February to June timeframe. And today I want to talk specifically about that period of time, the springtime, and it'll be a fairly descriptive presentation. As Matt said, the results are in quite a preliminary stage right now, but this is a first look. So a first look at the surface energy budget during spring. First, just to frame ourselves, some language from the objectives within the proposal. This is an NSF proposal through the University of Colorado, which was something that I collaborated with as a NOAA scientist. The language here says our objective is to enhance coupled process understanding of the thermodynamic and dynamic drivers of the sea ice mass budget to improve coupled models and increased forecast skill. So we're interested in the energy that's freezing and thawing the ice, and also the ice, the energy that's moving the ice around. And broadly, we could classify this into two different categories: a dynamic component and a thermodynamic component. The dynamic part being that ice moving around, that's led by Jenny Hutchings, Oregon State University, and that's not the subject of today's talk, although it's a very interesting part on its own. I want to focus today on the thermodynamic part. This is the vertical fluxes of energy from the ocean through the ice into the atmosphere through the ice back into the ocean. And some key words there that come up are atmos, ice, and ocean. So those are discipline teams within the MOSAiC framework. And so that's a natural collaboration here. Those teams did collaborate in order to capture that full vertical column of fluxes. We're actually going to hear from Don Perovich in the next talk from Dartmouth and Corel about the component that goes through the ice. Today, I want to talk about the atmosphere component, specifically the surface atmosphere interface, the surface energy budget, if you will, which is described by that red equation there, which is the net radiation, the sensible and latent heat fluxes. And today's talk is really going to focus around the net radiation part and not so much the turbulent fluxes. As Matt mentioned, there are a ton of observations from all around the MOSAiC array, but I'm going to focus specifically here on the atmospheric surface flux station, and I'll just describe that one. Matt already showed this presentation, this image here from taken by one of our colleagues, Michael Gallagher. It shows one of these flux sleds. So this, you can even see some skis on it here. It's mobile. We can push it around. We can pull it behind snow machines. We can fly it with a helicopter. This does it all. So this does the whole surface energy budget for it. So it does meteorology as well. And in that leg one, I worked to deploy these at the L site. So they were deployed at the distributed network at first, and that's where they stayed for the first half or so of MOSAiC. After that, we started moving them around and redeploying them strategically. As Matt said, that there were a lot of unanticipated changes, a lot of dynamics associated with the ice, a lot of movement of the deployment of assets around the ship. And so these moved as well. And for the talk, I'm going to take their data and I'm going to composite them. And I'll also say that there's a little bit of additional data from Met City that has been put in here to sort of fill some gaps. but that composite just for simplicity for today's discussion. And I'll start here with just the air temperature. So this is near surface air temperature beginning in the first week of October and going through the end of leg 4. Of course, we've also have leg 5 that is just recently finished, but of course I haven't seen the data from that yet. So we're just going up to about August 1st right now. In October, it gets colder. Until about March 3rd, 4th, that was the coldest day, minus 42, 43, and then rapidly warming. And that warming is really kind of punctuated. There's two periods there, and I'll describe that more in a moment. Beginning with this April transition on around mid-April, and then the melt onset occurring on May 27th, which I think becomes more distinctive if instead of looking at air temperature, we instead look at the surface skin temperature. So this is derived radiometrically from a set of pyrgeometers that are mounted on these sleds. This is the ice surface temperature. So then May 27th becomes the point when we sort of persistently hit the 0 C mark, and energy exchanges are now going into melting, in this case, the ice, and not into changing the temperature so much. That spring period, like I said, is punctuated, if you will, and it's just kind of in these two separate time periods, and that's before and then after the initial breakdown of the polar vortex, which occurred in mid-April. So prior to that mid-April event, we had almost consistently persistent north winds. Matt mentioned some of these. This persistent north wind really pushed the ship consistently towards the North Atlantic. And so we moved quite quickly in our drift. And the temperatures were close to minus 30 Celsius on average. Then there's some changes that occur seasonally in the stratosphere that occurring right there around April 13, 14 is the beginning of it. And that, I understand that the vortex was somewhat strong this year, and also, as I understand, a bit prolonged compared to most years. But it was really that initial change that we see in the atmosphere that provided the opportunity, the access, if you will, to air masses that are warm and moist from the North Atlantic to make their way to the MOSAiC array. And so you can see in the windrows for April 14th to May 27th, a completely different setup. So we have air coming from all sorts of different directions. And these southerly air masses are reaching the array, and they're impacting the surface energy budget. So a quick primer on the most basic sense of the net radiation budget. Let's just look at the long wave. So the long wave being the incoming radiation in the infrared radiation, minus the outgoing long wave radiation. And that net is usually negative. That's an expression of the cooling of the surface. When you put a cloud over that insulates the surface, it suppresses that cooling, and the radiation budget goes from being strongly negative to something close to 0. So the clear and cloudy skies appear in this bimodal state within the net long wave distribution. You can see in this histogram over on the right. And I've shown the different histograms for the different seasons of MOSAiC, and you can already start to see some differences in the transitions between the seasons, sort of incidental to today's topic because I'm really talking about the spring. One thing I wanted to point out is I think it's really interesting, this peak in the cloudy sky peak that occurs in the autumn at MOSAiC, which is shifted to these colder values. It should be quite close to 0, but it's more around minus 10 or minus 15. And this is either optically thin or very cold cloud cover, or it's an unusually warm surface, but the surface and the clouds are not coming into an equilibrium the way that you would expect them to. I suspect that oceanic heat is contributing to this through the thin ice cover, but I think that's just an interesting signal to look at moving forward. So looking again at the whole time series, going back to October, that red line is the surface skin temperature again. And then I've overplotted this, the net radiation. This is the net all wave radiation. So in addition to that net long wave, which in the wintertime you see here is persistently negative, surface cooling throughout the dark polar winter, we also have the net short wave added into this. So you can see in June and July, we get into very strongly positive values with solar input to the system. But During March and April, we get into a very kind of neutral scenario. And a caveat here is that some of those values in March are actually zeros, are actually not zeros, I should say, because it's actually missing data. So there are some data gaps in there that yet need to be filled. But once we get to the first week of April, we've got continuous data set again. And you can see kind of we're oscillating between positive and negative values there before we go completely positive on May 5th. But it's not till May 27th that we actually get get to the melt onset. So let's zoom in on that a little bit. Now we're into just this 3-month period between April and June. You can see in the left here some images taken before and after the onset of melt, just showing the character of the surface changes quite a bit. And this this period of April and May is sort of punctuated by these episodes of those warm air events. It's largely a synoptically driven, so advection of warm, moist air around low pressure systems centered around Greenland or Svalbard, or making their way into the high Arctic and impacting the array. So positive net radiation occurring periodically, and we actually do get melt, possibly on the 14th. It happens for sure on April 19th, and maybe a little bit on around May 12th or so, sort of indeterminate there as well. But we don't get the onset of melt, the true onset of melt, where you have persistent melting occurring, and again until May 27th. So a number of false starts, if you will, leading up to that point. So was this a shortwave process? And I think the answer is no. We do see a decrease in albedo from April into May. That's the green line. Those are daily averages. I think that that's largely an expression of the increasing sun angles as the sun is rising. So you have a changing incident angle on average, but there could be some aging snow that's contributing to that as well. You can see, however, that there's quite a bit of sunlight availability, even beginning in mid-April. However, there's a dearth of sunlight right around May 24th there to 27th. This is when that melt onset occurs. And you actually do get an albedo response from the surface at that time. It's masked a little bit in the daily plot because this transition into a strictly diffuse regime, this cloudy diffuse light, tends to raise the albedo, whereas the change in the snow grain morphology associated with the onset is going to decrease it. So these things are sort of compensating. You'd have to look at the clear days before and after that event in order to really see it. Now, we don't really see a marked change in the albedo until a couple weeks later in June, kind of second, third week. The caveat here being that this is from point measurements, and the albedo at this time of the year, of course, becomes very spatially heterogeneous. I think instead, this is a long process that's initiating this. So there was a storm near Svalbard at the time that drew air along its eastern flank up around to the array, and bringing temperatures near to the freezing point. So the cloud temperatures were really quite close to freezing. You get very overcast sky for a prolonged period of time, and you see a large pulse in the downwelling long wave associated with this. And that pulse quite quickly on its leading edge initiates the melt. And let's see, so that's the blue line. The yellow line is the outgoing long wave, which prior to the melt is responding to the change in the downwelling long wave. So when you get clearer skies, then it cools off, this lower downwelling long wave, and then that is associated with a cooling surface, which reduces the outgoing long wave as well. But as soon as you reach that melting point, then you can see the yellow line doesn't respond to the blue anymore. And this would actually be a negative feedback to the melting itself. It would tend to shed energy. And this is associated, of course, with the fact that energy is being exchanged latent within latent processes rather than a change in temperature. But there's some clearing that occurs in that kind of early June period. This general picture is quite similar to what was observed at Sheba in 1998, as described by Ola Person's paper 8 years ago now. And except, of course, for these melt episodes that occurred earlier, which I think are of interest. what is the role of the shortwave then? I suspect what we'll see is that the shortwave is acting to actually sustain that melt. So you need to trigger it with the long wave, I think is a reasonable hypothesis here. But then to sustain it, once that ice albedo feedback kind of gets kicked into motion, then you actually sort of need the net shortwave in order to work against that, that kind of pegged outgoing long wave, which is right at 0 Celsius. And indeed, we do see a decrease in albedo and increase in absorbed shortwave in the weeks following the onset of melt. And so that in conclusion, this was just an initial look at the surface radiation during springtime MOSAiC, and I think it illustrates some of the ways the atmosphere interacts with the surface. And melt onset occurs on May 27th, and for the MOSAiC array, and that's preceded by a number of episodic melt or near melt events that were associated with the seasonal changes, if you will, within the northern hemispheric large-scale planetary dynamics. I think long-wave processes are responsible for initiating this melt onset, after which the short-wave feedbacks on albedo become very important. But I think it would be interesting to take a closer look at some of these earlier melt events. And thank you.
Great. Thank you very much, Chris, for that really nice introduction to some of the science being undertaken to look at how the surface transitions throughout the year. Again, we'll reopen the chat box here, and if questions show up there, I will read them so that anyone who's on the phone can also participate. Otherwise, again, please feel free to use in the chat function or in the participant list, there's a raise hand button that you can use if you'd like to ask a question directly of Chris. While people are thinking about questions, Chris, I guess I'll start with a question, which is with respect to spatial variability. You know, we had one of the benefits of MOSAiC, or one of the highlights of MOSAiC, is that we had this big array of sensors, and I wonder to what extent you may or may not have had time to look at how consistent some of these messages are across different sensors and across the network.
I have not had that opportunity yet, and I think that opportunity is going to be, I mean, maybe Matt could speak to this a little bit. I think that that's going to be something that's really encompassed within Leg 4. One of the misfortunes of this particular, you know, the timing, if you will, is that the onset actually occurred at the Central Observatory during the Leg 3-4 transition. So Polarstern was not actually there. The observations I show, we kept continuous observations because we used those autonomous flux sleds, and so we were maintaining observations during that transition, but in a limited capacity. So we didn't have the flights during the onset. But I think Leg 4, the observations collected at that time will certainly give us a lot more information about the spatial variability component.
Thank you. We have a question in the chat from Hayo Icon, which is, sorry, I may have missed this in your presentation, but did you see any rain on snow events during the MOSAiC drift or during the transit?
Yes. Well, there was at least one fairly significant drizzle event. I don't know if I'd call it rain, but yeah, definitely liquid precipitation on, I want to say definitely one day and possibly 2 days. April 28th comes to mind as being a relatively important day for that.
Thanks. Also from Sandy Starkweather, how did the atmospheric sensors do with the ice conditions, frosting, fogging, clogging? Were you able to keep most of the data, or did you need to throw a lot away?
I am thrilled with the data retention rates regarding icing problems, with the exception of that May 28th, where we have refreezing of liquid precipitation on sensors. The de-icing was yeah, outstanding. I mean, I think that the whole system performed a lot better than we anticipated. There were, of course, isolated issues with certain instruments, but yeah, I mean, overall, I think that this is really successful in this respect.
Very good. A question from Mike McCracken. do you also have data above the surface, not just temperature, but variables like cloud albedo, cloud characteristics?
Yes, remotely sensed for sure. So there's the radars and lidars that Matt described, as well as a number of passive instruments. There's radiosondes as well. There are observations from tethered balloon, although most of that is more closely related to chemistry. And then, of course, there's the unmanned aircraft program, which was quite active during the second half of leg 3 through leg 4 and leg 5.
Very good. Another question coming in from Patty. It says, I like the expression of melt onset false starts, indicating that it is not a smooth process. We saw the same for the freeze up in AO 2018 MOCA. Was the spring melt onset similar to what was observed during Shiba?
In many respects, I think it was similar, yes. In particular, this idea of a synoptic event being the trigger.
Very good. All right, at this point, I think we're going to move to our last presenter of today before we open it up for broader discussion. And that presenter is Don Perovich from Dartmouth College from Thayer School of Engineering. Don is going to give some insight into initial observations of the snow and the sea ice during MOSAiC. So Don, please go ahead.
If you're a sea ice person, MOSAiC is the kind of experiment that you just live for. It's the kind of experiment you dream about. It's an opportunity to spend a whole year on the ice, just watching how a flow evolves over time. And it's also a chance to do it with people that are studying the atmosphere, the ocean, ecosystems, and biogeochemistry. And making it even better, you were there studying an important scientific question, and that's whether the causes and consequences of an evolving and diminished Arctic sea ice cover. So this is an incredible opportunity. Because of that, we spent a lot of time preparing for it to try to decide from a sea ice perspective, what were the key questions? What would be the approach to answer those questions? And the way we did it was modelers and observers working together, speaking with the modeling community to say, well, what are some of the gaps in the models? What are some areas where you need more observations? Are there processes that whose parameterizations need improving? So we really used models to inform the observational program. And now the hope is that the observations, now that they're over, that we will use those observations to improve models. So with these discussions that we had, we came up with some key sea ice questions. First of all, how can we characterize the spatial variability of the snow and ice covers? And what are the balances of heat and mass and sunlight? And then this new Arctic Ocean, what new properties, processes, and parameterizations do we need to understand in terms of properties of the snow cover, ice dynamics, and the partitioning of sunlight? And how does first year ice behave in the system? Well, we came up with an approach that the general approach is really summarized in this slide. We wanted to look at the temporal evolution, to take advantage of this year-long experiment, to see what changes occurred as you go from winter, where everything's cold and covered with snow, to summer, where the surface becomes an evolving mosaic of ice, water, and melt ponds. And we wanted to also, in each of those seasons, look at the spatial variability. In the summer, the spatial variability is pretty obvious with the ponds, but if you look closely at winter, you can also see variability in ice thickness and snow depth. And we wanted to do this in the context of understanding the two processes that drive sea ice, dynamics and thermodynamics. Now that's the broad picture. We also had detailed plans for observations. There were numerous ice cores taken. Monday was ice core day, where the ice team, the ecosystem group, and the biogeochemists went out and took ice cores. There were surveys done. surveys of snow properties, ice thickness, and mass balance. And these surveys were done on a number of scales. They were done with people walking, they were done with aircraft flying over, they were also done from satellites. In terms of optics, we made a series of measurements to look at solar partitioning, to determine how much sunlight was reflected from the surface, how much was absorbed in the ice, and how much was transmitted into the ocean. In dynamics, as Matt said, there was a lot of dynamics, and we were ready to measure it in terms of the motion, the internal stresses in the ice, and the deformation of the ice. And we were looking at leads, in particular summer leads. They're dark, they absorb a lot of sunlight, fresh water goes into them. What's the temperature and salinity structure of these leads? What happens to the heat going in? And MOSAiC was also an opportunity for remote sensing studies, both from space and also from the surface. We had an extensive coordinated set of measurements. And while MOSAiC was done on a number of scales, a lot of the work focused on the Central Observatory, basically the area around the polar stern as far out as you want to walk, scales of a few kilometers. And when you're doing a year-long experiment, you have to plan your real estate. And we came up with schematics, and reality followed those schematics. To get everything you want to have done properly, you need to have an effective use of zoning laws, which we did. Now, one of the things that's nice about a year-long drift experiment, you're there and you can learn a lot just by seeing things. Early on in the run-up to the field experiment, we often talked that we were going in the drift track of Nansen, the fabled drift of the Fram that started in 1893. And indeed we did. You can see here in yellow shows the drift of the Fram, and in red, the drift of the polar stern. The background white was the ice extent in September of 2019. You'll notice that we started further north than the Fram did because there wasn't any ice this year in 2019 where the Fram started. And you can see that actually looking at it, the timing of things was relatively similar. The Fram started on the 22nd of September. The polar stern drift started on the 4th of October. And they both reached the ice edge within a couple days, the 28th of July and the 30th of July for the polar stern. It looks very similar, but it wasn't, because the MOSAiC drift was around 10 months. The Fram drift was around 10 months plus 2 years. The drift of MOSAiC was much, much faster than the drift of the Fram 120 years ago. And that in itself is a fascinating scientific finding. It's been alluded to already that it's a combination. We have much thinner ice now than we did back then. And also the atmospheric circulation patterns were different this year. But with the combined data set that MOSAiC has, we can really pin down what's going on, what's causing this greatly accelerated ice motion. And you can also learn a great deal just by looking out at the ice. A series of panoramas were made looking off the bow of the ship. Here's one from July 13th after the polar stern had returned to the flow. And looking out, you see, some melting going on, some bare ice here and there, but it's still a flow with a relatively high albedo. Come back a couple weeks later and melt has really started. First of all, you see that the lead is opened up. This crack is opened up into a lead. Melt ponds have formed and they're covering a fair amount of the area. And also this revelation that the flow was really fairly heavily sediment laden. Come back a month later and you see that things have progressed even further. The ponds have gotten deeper, which you can tell by seeing that they're darker than they were before. They become more defined. The sediment laden ice is really evident all over this flow. And there aren't those small pieces of ice in the leads anymore because they've melted. And then you come back a couple days later and it's all over. You've reached the ice edge and the flow is broken up. So you can learn a lot just from drifting along for a year from looking at what the ice conditions were. But I don't want to give the impression that that's all we did. There were a large number of measurements being made, again, to look at the basic questions we had. And I want to just give kind of a sampling of some of those measurements. One of the measurements was looking at surface topography, and this was close during the winter. This was closely related to the question about what's the fate and redistribution of snow. Here's two examples of terrestrial LiDAR surveys, one on January 18th and the other on February 6th. These surveys covered an area of around 700 by 700 kilometers. The point spacing was around 10 centimeters in the horizontal, and the vertical resolution was a centimeter. And they're color-coded, basically showing a relative height. And you can look at it, you can see the ridges fairly easily. You can see some other features, which are snow. And the power of these, there are a number of these made of the same area sequentially, and this time series is providing data on the snow redistribution and also on ice dynamics. Just look at these two circles. Here's one where there was a lot of snow structure to it, a lot of snow dunes. Here's another area that was really very flat. A couple weeks later, after a storm, this area is now very flat, and this area has a buildup of a number of snow surface structures. We also made a lot of measurements of albedo, which is my favorite geophysical parameter. We set out a series of a few 200-meter long lines. Along these lines, albedos were measured every 5 meters, along with the physical properties. How deep was the snow? Was there a melt pond? If so, how deep was the pond? What were the characteristics of the surface scattering layer? Also, every 5 meters, a wavelength integrated albedo was measured, and also a spectral albedo over the wavelength range from 350 to 2500 nanometers. Like everything else, these lines were coordinated with other teams. One of the lines was set up adjacent to the ROV area that was making measurements of light transmission, and by combining those two gives an excellent picture of the partitioning of solar radiation. Just to show some results over here, this is albedo along one of those lines. And you can kind of see there's a lot of spatial variability. And that was one of the things we wanted to capture with this, is the spatial variability in summer albedo, which you can see is anything from 0.8 to as low as 0.2. Now, looking at this plot with the profiles from all these different days, it's a little busy. It can be a little confusing. We can get a sense of what's going on just by picking out the first day of measurements on June 20th and the last day of measurements on July 29th. And here you can really see the overall decrease in albedo during this time. These really low areas are places where there were melt ponds, and we can see the melt pond albedo decrease, in this case from 0.4 to 0.2, and that was a result of the ice in the bottom of the melt pond getting thinner and thinner, reflecting less ice. We can also take a look in another way and say, okay, what's going on over a spatial scale? And we did that by, for each day, averaging the albedo along this 200-meter line, and then plotting the time series of those averages. And that's what's shown here. Each dot represents the average for that day. The line is the median for that day. The box is plus or minus a standard deviation, and the whiskers are plus or minus 2 standard deviations. And these little stars or points that fell outside of 2 standard deviations. And there's a lot of details in this. It's really an interesting plot, but the key takeaway is overall, there's a decrease in albedo over the course of the summer. In addition to albedo measurements, one of the other things we wanted to look at is what was the mass balance of the sea ice. And during MOSAiC, over 120 of these sophisticated mass balance devices, ablation stakes and thickness gauges, in other words, sticks and wires, were deployed. It turned out to be, as we've heard before, a rough neighborhood. There was a lot of deformation. We lost a lot of stakes to pressure ridges. But here's some examples from the Fort Ridge site. What's shown here is a time series from January through July. The top plot shows snow depth and these are results from 9 different gauges with everything, color coded. And what we see is in snow depth, there's a lot of spatial variability. If you look at it closely, there's a general increasing trend during this time, but there's a lot of variability from blowing snow. We also have a time series of ice thickness during this time, and we can see at all the sites there is steady ice growth, and then we were just beginning to see the onset of summer melt. And we can take these data and just look at how much ice growth was there from January to the end of the growth season, and we get values from 80 to 110 centimeters. And then we can use this data to start to explore possible relationships. For example, is the amount of winter ice growth related to the initial thickness? And these are points for these 9 cases. And you can see there's something of a trend for a number of the stakes, but then there are a couple outliers which show there's more to it than just the initial ice thickness. And again, we have results from these stakes in a number of different locations. Now, in some of the earlier presentations, we heard about the distributed network and some of the remote sites. Those remote sites, in conjunction with the atmospheric measurements that were already mentioned, we put in autonomous sea ice mass balance buoys, and those buoys also measure barometric pressure and air temperature, but they were mainly there to look at what was going on in the ice cover. And you can see here, we get a time series of snow depth. We also get see how the ice is growing and see temperature profiles in the ice and how the cold front propagates down. From this information, we can get a time series of the growth rate and see when MOSAiC started, the ice was still melting. It spent the first few weeks of MOSAiC melting, and then eventually it got colder. The temperature wave propagated down to the bottom. We had growth. The maximum growth was in January, tapered off for the rest of the winter, and then sometime late May, early June, we went back over to melting of the ice. There's this interesting feature here, which I originally thought was just some bad data points, but it turned out measurements made at the Central Observatory at the same time showed that there was frazzle ice formation in the upper ocean, which I think was a surprise to most of us. It's something that's associated mainly with Antarctic sea ice, but we saw some of it here as well. So one thing about this data set is from the very beginning when we were talking about MOSAiC, the idea was the data are the legacy. MOSAiC was in the planning stage for over a decade. The field work took a year, but the data will be used for decades to come. And from the very beginning, there was an emphasis on promoting data fairness and accessibility, working on observation to archive, to the point where the data was being archived on the ship as it was being measured. And so the goal is a complete data set that's archived and published with full metadata. And finally, what's next? I've had people come up and say, wow, MOSAIC's over. What are you going to do now? Well, the field experiment is over, but the excitement continues. I mean, we have just an incredible data set to work with. First of all, just to reduce the data, then analyze the data, then begin to integrate the data sets across different areas, and then to synthesize the data, and finally to incorporate it into modeling. The excitement is just beginning. Thanks.
Thank you, Don. That was really nice. As before, we'll open up the chat and the participant list. If you want to ask questions, please feel free to raise your hand or add something to the chat. Looks like Hayo has his hand up. Hayo, if you can unmute, go ahead.
Hey, thanks, Don. That was great. Just a little addition. I just wanted to clarify, because I know Marc Augier, a PhD student here at UAF, who was working with the biogeochemistry team, did a bunch of sea ice core stratigraphy analysis. And the ice that formed in January wasn't just ordinary fragile ice. I mean, it was true platelet ice with crystal sizes on the order of several centimeters or larger. The AVI ROV had a great perspective on that as well. And so I see this as an interesting observation because that's the first in situ observation of underwater platelet ice forming. There's a paper in GRL that came out that was led by lead author Chris from AVI. And the question I had for you, though, is what's your sense in terms of true fragile ice? So fragile ice forming in leads and being swept underneath the solid ice cover and contributing to ice growth over the course of the year. Can you speculate on that at all?
I mean, I can certainly speculate on it. I'm not sure. I would think that that would be smaller. I mean, I was really amazed when you know, I saw the results from this platelet ice formation. You know, it was reminiscent of what people see in the Antarctic, and I don't think that were that were things that were swept out from under leads. You know, what do you think about it?
Well, I'm not sure myself either, but certainly if you look at Christian Kotlin's paper in GRL, you know, this does potentially seem to be a much more important, the underwater platelet ice type formation, important process in terms of accretion in the wintertime than fragile ice formation in leads. But I mean, that's something maybe to look at in more detail once you guys consolidate your data.
Yeah, and I think one of the questions, and we may not be able to answer this, is this something new, or was it always there and we just weren't there to see it?
Yeah, thanks, Don, and thanks for the question, Hayo. We have a few more questions coming into the chat here. One from Wilbert Weyer asking what the source of the dust on the sea ice was.
I don't know.
I think one of the presenters in the early career presentations earlier today was saying that the ice had originated as landfast ice, and that some of that was sediment that had transported with the ice. But I'm just repeating rumors at this point. So I think others will probably have more insight into that.
If I had to guess, I would guess that it was sediment entrained in the ice rather than dust blown over the ice.
Okay. Another question from Sinead Farrell, asking if you could comment on whether you were surprised by the thin snow cover for MOSAiC, and she noticed that there was only one observation with snow cover greater than 30 centimeters.
I wasn't really surprised by it, and I think we're still processing that. I mean, there's some really good information from the snow surveys, and I think will provide a much better insight to what the actual aggregate snow depth is.
Another question from John Yackel asking, roughly speaking, what proportion of snow and ice physical property measurements collected during MOSAiC, both from the Central Observatory and distributed sites, would be from first year ice versus second year ice versus multi-year ice?
I don't know the exact fractions, but I know both. There was a focus on measuring both types. And I know for the albedo measurements, there are lines on multi-year ice and lines on first year ice. And I think there are also survey sites on both types of ice. So there was definitely a real effort to get every ice type that was there.
Thank you. Another question about the variability of snow depth. saying, I saw that one of your slides showed a lot of variability for snow depth among the many gauges, while ice thickness appears very consistent among the sites. Why? It was a rather small area compared to IMBs all over the Arctic.
Yeah, I think a lot of that is just the snow blowing around. And if you look at those, while there's a general trend of increasing snow depth with time, you can look at one data point and the snow depth goes down, and then a neighbor goes up because it's just being redistributed. And I think over the course of a winter, that may all balance out to some extent.
Okay, thanks, Don. And a couple of comments just confirming the sediment transport and some of the interesting things. Matt's talking about rock starfish, sea plants, and others, a collection of Siberian treasures. So it sounds like there was a lot to be found out there on the ice. Don, I'll say quickly, I really appreciate your albedo slide. And I think, as you know, we had one of our systems flying around to measure albedo, and Radiance Calmer, who's on the call or who was on the call, is starting to dig into that data set. I would really love to put those observations next to some of those from the albedo line that you were showing.
Yeah, that would be great.
There was another question in the chat, but it just went to me. Was there also snow water equivalent measurements along the depth?
Yes, they were part of the overall snow program. There were snow pits, snow water equivalent. There was a snow micropen that was used repeatedly to look at profiles of snow properties in terms of grain size and strength. So I think going into this, there was a real emphasis on understanding the snow because of the importance that it plays, one, in terms of, well, slowing down ice growth in the winter by being a thermally insulating layer, but then making up for it in the spring by reflecting sunlight and keeping the surface cool for a while.
Yeah. Okay, we have about 10 to 15 minutes left here, and there continue to be questions about the data, and I think there's broad interest in the data set, which is great. So I think we'll transition into a broader discussion. Certainly, if people continue to have questions about the materials that were presented, that's great. But also, if people have more general questions about MOSAiC, and maybe we'll lead with this question that came in about the data repository. So it asks, does MOSAiC have a shared data repository or separate as per the funding agency's requirement? And I don't know, Matt, if you want to address that one or others.
Yeah, I can speak to that. So there's a number of things about data that are really important. And certainly Don's comment about the data being the legacy, that, you know, that's definitely the first order there. So MOSAiC does have a whole data archive structure through Pangea, which is hosted by the Alfred Wegener Institute. And that's kind of the primary place where data will be archived. But there are a number of other institutions that have their own archives. So for example, the Department of Energy ARM program has a fantastic archive, and their data will go into that archive. And many of the NSF funded projects will archive data through the Arctic Data Center, and will create some cross-linking to make sure that everybody's happy and all the metadata is cross-linked accordingly. So there are some things set up like that. There was also the comment earlier on about data availability, and this is a really important one. Through some serious negotiation, we had to take a lot of perspectives into account here and arrived at a place where data right now, all the MOSAiC data, is available to the MOSAiC consortium. And so these are people, projects that are endorsed by the MOSAiC, MOSAiC process here, and they're part of the consortium. So your ticket as a consortium member is that you get all the data early. For the first 2 years, it can remain within the consortium, but after that 2 years, it has to be publicly available. Now, anybody that's a member there who's creating data can make that data publicly available earlier than that. And I know, for example, again, the DOE, their data is already available publicly, and many NSF projects also are providing their data publicly very early. And I myself encourage that for the community, because I think personally that the more people we engage earlier in the process, the more scientific impact we're going to have. And so that's kind of the overall picture. So within 2 years, all the data will have to be available. And you know, in the time between now and then, the data will be coming available as the investigators make it that way.
Thanks, Matt. I think that's a really important point, and certainly one that's of interest to this group. Again, IARPC is all about developing collaborations and opportunities to extend efforts that are supported. I wonder along those lines whether there's any, the projects, at least on the US side, that have been funded as part of MOSAiC have largely focused on collecting the data, on processing the data, making it available, and some science as a result of those data sets that have been collected. And I wonder whether there is anything to talk about here, given that this is kind of an interagency setting, about trying to organize at some level the kind of analysis and science piece of it from a funding and maybe science team perspective, and how you envision, how the group envisions that moving forward in the coming decade or more, as these data sets, which are huge and rich, are explored. I don't know if people want to weigh in with their thoughts about that.
I don't want to be the only one answering here in general, but this is such an important time. I mean, I'll just say it straight up, and I know there's some funding managers on board here, that it's no problem funding big, exciting projects. The community does that, and we do that routinely. But funding the analysis is something we struggle with as a community. And I think that we really need to figure out how to do a better job of funding the analysis, because there's so much investment in collecting these data, and they're really valuable data, and we need to invest in the analysis so that we can get the most out of that. And we had this really fantastic discussion on the way home from Leg 4 with many early career scientists, where we're talking about sustainable science and how do we get the most out of this. And really, that was one of the resonating factors, is that we have to get the most we can out of the data that we have right now. And so I would certainly hope that there's encouragement, and hopefully through IARPC and other mechanisms, to both have funds that are available, but also find ways to creatively encourage the community to engage in those data. And that's in part on the funding agencies and in part on the community of scientists and leadership of MOSAiC. And so I hope in partnership we can really push that forward.
Yeah, thanks, Matt. I mean, I think the point about IARPC's role in this is a good one, and I think in the current research plan there was a performance element focused on the planning, preparation, and implementation of MOSAiC, and I think perhaps it makes sense to think, as we're developing the next 5-year plan, how MOSAiC could fit into that framework to ensure that this data set is used to its optimal extent. I see a hand up. Looks like Patty. Go ahead, please.
So I'm going to support what Matt is saying. As Don and several others here know, many of us have been involved in long-term collection of data as part of the Arctic Observer Network for funded by the US NSF. And they have changed the model, but for the longest time, the data analysis was not part of the project. And we ran into lots of difficulties, right? Getting the community to understand that working on data that has been previously collected is a great idea. Instead of being told, you should have analyzed your data when you were collecting it, but we weren't funded to do that. And so everyone needs to, in whatever nation they are, to talk this up with the funding agencies. I couldn't agree more. Otherwise, there will be great data which have been collected, like the OB or all of that atmospheric data, and we won't take advantage of it with lots of lessons learned and lots of information. So whomever those of you who are in these committees and things now, I did my part, please insist, talk it up. It still drags on. Thanks.
Thank you. I see Ulla's hand. Ulla, go ahead.
Yeah, I just want to reinforce also what Matt and Patty said. We've already spent a lot of money collecting this data. We should do everything we can to get all the science and information out of the data set that we have now collected. And so whether that was anticipated before it was collected or not doesn't really matter. I think the important thing is to make sure we get the everything out of the data set that we can, because it's so much effort to get this data. We really should spend additional funds later to do the appropriate analysis of it.
Thank you. Yeah, I mean, it is important, of course, to recognize that there has been already money supporting science as part of the projects that have been funded and as part of some newer projects through the Department of Energy and other groups. But again, I think there are opportunities, particularly within the IRP framework, to ensure that that's done efficiently moving forward, because this data set is much bigger than a handful of projects, right? This is really a broader community effort that we should continue to support. Additional comments? Matt, I saw your message. Thank you for joining us. Appreciate it. And if there are additional questions, I'll pass those on. Additional questions or comments from the group? Ulla, go ahead.
Yeah, I sent a little message here, but on the chat, but I'll just state it here. Just an extension to Chris's presentation. As he mentioned, he didn't have any data from leg 5 yet, but he mentioned how the freeze up process, the melt process was came in pulses in events until it was finally over into a full onset of melt event. And that's how the freeze up process also happened in the fall. There were pulses of freeze up that then went over into a full freeze up in early September. And even that full freeze up was briefly abbreviated with a rain on snow event. So of basically 24 hours of additional melt later in September. So again, this pulsing of events, generally synoptically driven, seem to be the characteristic of the freeze up as well as the melt that Chris talked about.
Thank you, Ulla, for the additional insight. All right, we're approaching the end of the meeting here, and we typically like to save a couple minutes at the end so that the collaboration teams can advertise their next month's meeting. And I'll check in also with Anne and Meredith to see if there are additional announcements from the IARPIC side. Let's do that first, actually. Anything from you guys?
Sure, I'm going to post in the chat here information if anyone is interested. We had 3 other MOSAiC topics this month, so they're in the chat. You can access those recordings. The early career recording that Heist was alluding to earlier is not yet posted, but will be. So those are there for everyone.
Great, thank you, Meredith. At this point, I think we'll quickly go through the collaboration teams, and I'll try to find the appropriate leads for each team to just give a quick announcement about next month's meeting. For the Atmosphere Collaboration team, we're going to do something that focuses on AGU, and we're working out the exact details of that. But given that AGU is asking that presentations are done early on this year for the virtual format, we're going to try to set up a meeting that helps to highlight some of the kind of Atmosphere Collaboration team relevant talks and sessions that will be occurring at AGU to build up some community excitement around those and hopefully give people some insight into what they might look out for during the meeting. Let's move next to the Sea Ice Collaboration team. Let's see, I think Janet was on, or anyone who is a Sea Ice Collaboration team leader, if you'd like to speak up, please go ahead.
I don't think that the Sea Ice team will be meeting until late November, and it's my understanding that they're still in the process of working out what they'll be focusing on.
Okay, very good. Thank you, Meredith. Physical Oceanography team, Wilbert, do you have any announcements?
Yes, so we're currently working on organizing a joint meeting with the Arctic Observing System subteam on long-term observations of the gateway transports. So that should be on November 5th, but that's we're still working on figuring out the details for the meeting. Thank you.
Great, Thank you, Wilbert. And from the observing sub-team, are there any additional announcements beyond that one?
Hi, yeah, this is Sandy. Next week, the observing team is going to be meeting for as the National Committee to SAON meeting. So it's our international roundup where we're going to be talking about frameworks, progress on the road framework from the SAON side. We're going to be hearing from Roberto Delgado about the USA on board and what they've been working on. And we're going to be hearing from Peter Pulsifer about some of the hackathons that the Arctic Data Committee has been leading. And that's hopefully, I think MOSAiC would be a great subject for merging with their hackathons process. So encourage everybody to check that out next week.
Great, thank you, Sandy. I agree. That would be a nice opportunity to leverage this project and again, continue to develop collaborations. Finally, the modeling team. Anyone on from the modeling team who would like to make any announcements?
Yeah, this is Robert again. I'm on the modeling sub-team also. I don't know what we have planned for November, but I think in December, we're still thinking about a follow-up on the gateways team, but then from the modeling perspective. So that's also something that we're still collaborating on with the Physical Oceanography team. Thanks.
Great, thank you, Wilbert. All right, with that, we are at the end of our hour and a half. I really appreciate everybody's participation and involvement in the meeting, and especially to the presenters for giving some very nice introductions to what is coming out of MOSAiC on the air, ice, ocean side of things. So thank you all for being here. We look forward to seeing many of you again next month in many of these collaboration team meetings, and we look forward to that. So thank you. Have a good day.